Voice of the Sea, learning from experts across the ocean.
Welcome to Voice of the Sea.
In this episode, we're talking with oceanographer Brian Pope and geologist Christian Miller. By sampling different water depths and comparing them to the metal isotopes that are found in the tissue of fish, Brian's work can build an understanding of how metals are accumulated in the fish that people like to eat. We start off on board the research vessel Kilo Moana on one of Brian's research trips, where a crew of scientists and technicians go to sea for weeks at a time to study the ocean. On board, Brian is going to show us his mobile clean lab, and then we'll be at the Pacific Ocean Science and Technology Building at the University of Hawaii at Manoa with Brian and Christian to see how they deal with the samples back on land.
Hi, let's go in here where it's nice and clean. My name is Brian Pope. I'm with the University of Hawaii in the Department of Geology and Geophysics. You've now just entered our trace metal clean bubble. We erected this plastic tent to keep all the metals out. We have a hood here that filters all the particles out, and it gives us a flow of really, really clean air over these filters that keeps this room nice and clean. Let me show you some of the equipment that we use to sample water. We get it out of its protective bag. This is called a GoFlow bottle. It's different from the Niskin bottles that we saw outside in that the opening to it on the top and bottom are made so that it stays closed when it goes through the water. You can see when this spins, there's an opening there, and every 90 degrees it alternates between open and closed. The reason why we want this bottle closed when we send it over the side and into the water is that the very top surface of the water has a lot of contaminants in it, especially metals. We're on a metal ship, and there's metals that are always being eroded off that ship. It's like measuring iron in seawater is very important, and we're on this iron ship. It's a ship made of steel. So we don't want that contamination in our bottle. So we use this special bottle. It's a little bit more difficult to use than the 24 bottles on the rosette outside, but it stays clean as it goes through the air-water interface and the upper 30 feet of the ocean. We know how deep the bottle goes, and by sending what's called a messenger down, it's a coded weight on that line. It comes down, it hits this, and voila, closes the bottle, and we get our sample. And we can then bring the line back up with the bottle and take this bottle, this GoFlow bottle, into the laboratory and sample it under these clean conditions that we've created with our trace metal free bubble. We're sampling mercury in this case, and it's mercury that's dissolved in seawater. We're interested in the concentration of mercury as a function of depth because we've seen mercury changes in fish that feed at different depths within the ocean. And we want to know if that's what's driving the concentration gradient in fish, whether it's a concentration gradient in dissolved mercury. When we bring our samples back here too, we want to be really, really careful about any contamination from the environment. We have special clean labs that we use only for our mercury analyses. We don't have to worry about that for nitrogen and carbon. There's no contamination that we have that's a problem. But if mercury gets in from either from the dust on the floor or from fluorescent lights, there's a lot of mercury in fluorescent lights, that's a problem. So we have to use special clean lab to do that.
Well, can we take a look at your clean lab?
Sure.
All right. The Clean Lab was built in 2006 to provide an environment free of trace metals for researchers to study geology, volcanology, and the environmental effects of human activities.
You guys should, when you guys are ready to step over onto here, you can put your feet inside some of these. One thing to be aware of these is that the floor can be slippery when you're wearing them because there's very little grip. So there should be a pair for you and a pair for Kenisa.
Thank you. And we just go through there.
Usually just put these on over your
That's
overhead.
Yeah. And just a quick question, have either of you been swimming this morning in the sea by any chance?
No.
Perfect. The reason I ask is because we do analyses of strontium in this lab, and strontium is the 5th most abundant cation in seawater. So it's a potentially large contaminant if you walk in here with sea salt on your skin and in your hair.
You look nice. Dr. Pope.
Why, thank you, Dr. Duncan.
We are gowned up. The shoes are off. We got footwear that's worn only in this lab because obviously the bottoms of your feet and your shoes are very dirty. And the simple fact is we are covered up as much as possible because once we go inside, we are going to be the dirtiest things in the lab. We're going to be dirtier than the floor. We're going to be dirtier than the counters. And so as we come into the clean lab, we try and make things progressively cleaner. So, there's a line past which we do not wear shoes. Then once we come in here, we always gown up and get ready in this room before heading in there. And we always be sure to step here on the sticky mat so that whatever particles are on the bottoms of our feet and of our booties get taken off, and so that we don't take them into the lab. Also, in every room in the lab, there will be one of these, which basically describes the air pressure. And the thing that makes the clean lab so clean and allows it to stay so clean is that the inside is at a higher air pressure than this room. So any dirt that does fall to the floor gets swept out by air moving underneath the door, and this room is higher in pressure than the one out there, and the one out there is higher than the hall. So as you go in farther and farther, it should get cleaner and cleaner.
And why do we need to keep it clean?
And so we look at elements in rocks and other geological materials like seawater that are present in part per billion level quantities. And so if you're looking at something that's a major rock forming element, like magnesium, you don't have to worry about contamination. We could do that. You could do that science on the counter in your kitchen and not worry about contaminating it. But if you're looking at something like lead or iron or mercury in seawater, you have to be very, very careful. I mean, it's very difficult even to collect them because you're collecting them from a metal vessel. So it's just once you get to this part, you don't want to introduce any contamination here if you've managed to keep things clean all the way through. So,
Step on the sticky mat again, please. On the ship, we had a hood like this, but it wasn't anywhere near as clean as this laboratory, and we didn't have the same kind of a pressure control to keep the contamination out. So if you remember, we created a plastic bubble around it to try to keep any contamination to a minimum. And any time we opened the filters that we were going to analyze, we did it under one of these hoods. And what is special about these hoods, Christian?
So we try and keep everything clean, and we try to make things get progressively cleaner and cleaner. So this room is cleaner than the room where we gowned up, which is cleaner than the entranceway, etc. The cleanest parts in the labs are inside the hoods because they are constantly fed clean air through HEPA filters, in this case in the top, up here and up here. And if you'd like to see one of these filters, what they look like, there's a large one right there behind the plastic grating. So this is all one large air filter And above it are 3 fans that are blowing, pushing air from the lab, from the top of the lab where it's clean and not dusty, through the filter into the hood, and it then comes over the surface of the hood and onto the ground. So again, the farther in you go, the cleaner it gets. So, you know, the back of the hoods are cleaner than the fronts of the hoods are cleaner than the air in the labs.
So we would do all of our chemistry with ultra-pure chemicals in hoods like this that have filtered air continuously supplied that are really, really clean. They're mercury-free.
And in your case, it's not because the mercury would hurt you, it's because the mercury from the environment would contaminate your samples.
Exactly.
So we have a series of these hoods. So this one is also a clean hood, but it also exhausts, and you can hear the fan going. So you can see there's a very gentle draw of air into the hood, which is so we try and work with our acids in hoods that exhaust, whereas we can do other kinds of work in that hood over there, for example, which does not exhaust. But again, also a clean hood. In this one at the moment, I'm distilling hydrofluoric acid in an elbow still. Right there are 2 hydrobromic acid stills, the orange liquid.
The Curriculum Research and Development Group in the College of Education at the University of Hawaii at Manoa. CRDG's training roots go back over 40 years. Through professional development programs, curriculum workshops, research on teaching methodology, individualized school and district training, and so much more. The Curriculum Research and Development Group, improving schools, improving education. CRDG.
Welcome back. We're in the Clean Lab at the Pacific Ocean Science and Technology Building. The Clean Lab facility is licensed by the Nuclear Regulatory Commission for work with radioactive materials and tracers, which researchers use for precise analysis of metals in rock, volcanoes, and even seawater.
A couple times a month we have to come through, wipe down, test to make sure that the radioactivity levels, that we haven't spilled anything. So I mean, these are not unsafe levels. You know, it's completely safe to be in here. It's safe to work with these materials. But when you work with radioactive spikes of uranium, for example, the Nuclear Regulatory Commission likes to keep very, very close track of that. And so that is why we do it, not because we are looking at radioactive contamination of samples or anything like that, but just because if you want to work with these materials, those are the rules you have to follow. And that's just the way it goes. That's just the way it goes.
What do you use the radioactive spikes for?
So we call them a spike because we quite literally spike a sample. We add, for example, this 228 radium spike to a sample which has radium in it, but because the half-life of this is so short, 228 radium doesn't exist in nature. So we add the unnatural radium to natural radium, and we're able to measure its isotopic ratio very, very precisely, and that is the best way to get at the concentration of radium in natural samples, is by what's called isotope dilution. You take isotopes that are enriched, mix them with natural samples, measure the isotopic ratios very, very precisely, and get a very precise determination of the concentration. It's the best way to do elemental concentration analyses in geological materials. The distillation units are in there. That's this large item here. Sorry about the poor light, is a quartz still. So this produces very, very clean water already. It's called a millicue system. Whoops, here we go. And you can see here that it says that the cleanliness of the water is what's called 18.2 megaohms. So that's a measure of the resistivity. And the more stuff there is in water, the more dissolved constituents, the more conductive it is, the less resistance it is. So a high resistivity is indicative of very clean water. And from there, we fill up this carboy and then fill this quartz still. And so this is basically QED water, ultra pure water. The amounts of lead, for example, in that water is less than a part per trillion of lead in the water.
Wow.
So
now, why is lead more susceptible to contamination than mercury?
2 reasons. It's a volatile element, so if it heats up, it will volatilize and it will evaporate. But the main reason is because of tetraethyl lead additives to gasoline that were used for decades in North America. So, you know, tetraethyl lead used to be an anti-knock compound in your gasoline, and so basically it polluted the environment with an anthropogenic.
There's a legacy of that still with us.
Still with us. Also, I mean, you know, lead paint. I mean, it's a very, very common metal in the natural environment and a very useful metal industrially. So it was used a lot industrially.
With mercury, we worry about fluorescent lights because of all the mercury in fluorescent lights. They're high in mercury. So we would want to change our light bulbs ourselves.
Oh, great. I hadn't thought of that. Yeah, so, you know, he worries about light bulbs. I worry about people swimming before coming into the lab. It's, you know, it's all what you do and what you can live with.
The University of Hawaii's Sea Grant College program focused on Hawaii's coasts and its communities through sustainable development, safe seafood supply, sustainable coastal tourism, hazard resilience, and healthy coastal ecosystems. Hawaii's Sea Grant.
Welcome back. We're checking out the highly sophisticated Mass Spectrophotometer used by researchers in the School of Ocean and Earth Science and Technology at the University of Hawaii at Manoa. The Mass Spectrophotometer is used to analyze the chemical components of samples, from fish tissue to volcanic rock to environmental pollutants. By comparing the different forms of elements, known as isotopes, researchers can determine where specific chemicals are coming from.
This is a mass spectrometer. And so when you think about like a prism, just a light prism, it separates the constituents of light based on wavelength and produces a spectrum. This also produces a spectrum, but here we start with an ion beam, like a beam of charged atoms. And instead of separating them based on wavelength, here we separate them based on their masses. So most of the mass separation basically happens right in here. It's inside here is a large electromagnet, and as a charged particle goes through a magnetic field, it'll deflect, and the amount by which it deflects is a function of its mass and the radius of the magnet. So the heavier it is, the less it will deflect. The lighter it is, the more it will deflect. And so in here there's a series of Faraday cups all lined up at specific intervals. So all the beams of, let's say, an isotope system like neodymium can all be collected statically, so without hopping, without moving the magnet around. The ions are made in here, which is what we call the source. And if you look through the window there, you'll see that there is what appears to be a green flame. It's not a green flame, it's actually a white hot flame. You can look right in there if you'd like. But the glass is tinted because it also throws off a fair amount of UV radiation. So a plasma is essentially, in this case, it's a flame, about 7,000 degrees. And we make it with what's called an RF generator. We pump radio frequency radiation into a coil through which is passing a large amount of argon gas, and that is sufficient to excite argon, which is normally a noble gas, which doesn't form ions, but it can actually ignite something that normally would never burn. the flame that you see was actually right here. And when you're working with basically a glass torch and a 7,000 degree flame in close proximity, if the gas flows aren't right, you can melt the torch. It doesn't happen often, unfortunately, but it will happen. And this is ultra pure glass as well. So one of these runs for about, I think, $300. So it's extremely high purity glass, and sometimes we get unlucky. And so because it's a 7,000 degrees, it basically takes an atom of anything and makes it into an ion. Some things are much harder to ionize than others. Strontium is very easy to ionize. Osmium is very difficult. But when you're dealing with an ion source at 7,000 degrees, anything will ionize, including things like argon, helium, neon. So you'll get peaks of all of it.
So in the mass spectrometer that we saw that measured nitrogen, we're only using a small voltage to do that, 70 volts. And it's at low temperature because it's easy to ionize something like carbon dioxide or nitrogen. It requires something much greater than that to ionize a metal like neodymium or mercury. So it takes a special instrument like this. Christian?
Yes.
What is the accelerating current to create your ion beam, to push it through your magnet?
At the moment, what does V1 say, HV1? 6,000 volts.
6,000. So the accelerating voltages are about the same. We use 10,000 volts on ours. We have other instruments that only use 2,000. But the principle is the same, but the little details and the price is different. With mercury, what we do is we burn the sample in a really clean environment in the clean lab and capture that as a salt in a solution. And that solution containing the mercury from a fish or from a crustacean, a shrimp, is then fed into the plasma to ionize the mercury. There's a little bit different details. There's a hydride generator, which is required for the mercury analyses. But it basically is to do the kinds of things that we do with gases. We need to create an ion. We need to create a beam from that ion and separate the masses and then collect them. For metals, it's much more difficult, and it requires temperatures of 7,000 degrees.
And that allows you to see the different forms of mercury that we were talking about.
Yeah, the different isotopes of mercury.
Exploring Our Fluid Earth is a dynamic curriculum developed by the University of Hawaii's Curriculum Research and Development Group, teaching ocean science concepts through the disciplines of physics, chemistry, biology, and ecology. Exploring Our Fluid Earth is now available freely online. Find out more at exploringourfluidearth.org.
COSEE-Island Earth is working to establish new avenues for connecting research scientists with educators and communities. COSEE-Island Earth is working to enhance the science and ocean literacy of our island residents and visitors. COSEE-Island Earth is working to connect scientific research, traditional knowledge, and ocean policy. COSEE-Island Earth, bringing together university, government, research, and community partners to enhance ocean literacy and engage all ocean users in stewardship.